So you see here the steps. First, you have the dynamic modular ratio. It's going to be slightly different from the static one. You have here a factor, you divide here by a factor of 1.35, and the number that you're going to be getting out of it, you just use it as is. There's no rounding up or rounding down or cutting off the, the fraction. You don't do this. You just use the number as is. And we're going to see this in a second. And then after that, you do the joist panel mode, find out deflection for some weight, and we need to consider a kind of reasonable amount of load besides the dead load. Because if you're talking about vibrations, vibrations can happen when you have people present there. And after this, you do the frequency, initial frequency based on this deflection. And certainly you need to find out ds and dj, because you need to find out, we're going to call it here, effective weight that you need to consider in your analysis. You do this first for the joist, and then you do it for the girder, and you do the combine. And then after that, you do the combined effect. And once you do the combined effect, now you have the final weight that you're going to use in your analysis. At this point here, you figure out the amplification, which is AP divided by G. It's going to be the acceleration of the floor system in the vertical direction. It goes up and down as a fraction of G, the ground acceleration. And then you compare it with the half percent. The half percent, the one that we were talking about. So I'm looking here at this example. In this example here. So it says that this is going to be an office. It's going to be used for an office building. Structure system supports paper office built out. So we understand here how much beta factor we need to consider for it. It says here, you assume live load is 11 PSF. So the issue is you need to find out the vibration when you have a live load of 11 PSF. So on the top of the dead load, you need to consider additional of 11 PSF. And with that, you can figure out the total weight applied as an effective weight. Let's say that there is a ceiling. So ceiling is going to be important. Mechanical equipment below was an assumed superimposed dead load of 4 PSF. So the additional dead load here is going to be 4 PSF. And of course, you have mechanical ducts and equipment, you have a ceiling, and all of that is going to be adding up to the beta factor. Spandrel girder supported by exterior cladding for vibration. This is good. And then the building is 5 bays in east-west. So they give you some information here so that you figure out the total width and total length of the building. And as you see here, there's not like a big hole in the middle or on one side, like the example we have considered. It's going to be just continuous in both directions, east-west and north-south direction. You have the slab is going to be 5 1/4 inch total depth. And as you see here, you have lightweight concrete, 110. F prime C is going to be 4 KSI, 2-inch deep deck, which means the deck itself, the metal deck, is going to be 2-inch, and the concrete above it is going to be 3 1/4. This is going to be a little different from the one that we used to use. We used to use W3. Here it says use W2, and the top of it you have 3 1/4 to a total thickness of 5 1/4 inch. Assumed self weight of the deck is going to be 2 PSF. And then it says the beam is grade 50, A992, the ACM. Some information here also is provided to you, the spacing between beams. The spacing between beams is going to be 10 feet. The beam size, W10 by 35. The girder size is going to be W21 by 50. Okay. The spacing is going to be 30 feet. This is going to be for the column, which means the span here of the girder is going to be 30 feet. The span of the beam is going to be 35 feet. And here it is, 2 plus 3 1/4, you have 5 1/4 sitting on W18 by 35. So what I'm doing here, I'm just repeating the same information the data provided to us. Just repeated here. 5 bays and 3 bays. Type of steel. Live load to be used. The ceiling, additional dead load, slab thickness, and the deck weight is going to be 2 PSF. Same picture provided to us in here, just a larger picture of it, so it's going to be more clear to us. It shows the beam size, the girder size, the span, and the spacing between beams. Same information provided to us, 992. It means F sub Y is going to be this 50 KSI, F sub U is going to be 65. The beam size, beam information, you can just look it up from the steel manual. You have here the beam parameters. Same thing for the gilder. And then after that, we're trying to find out the floor width and the floor length. And we went through this exercise before. Now, how much is going to be the length? In this case, length is giving direction of the beam. So all the beams are spanning this way. So the length is going to be 3 times 35 is going to be 105. And the building width is going to be 5 times 30 feet. Where do I get the 30 feet from? It's going to be from here. It's going to be 30 feet times 5 is going to be 150 feet. This is going to be the width of the building. So we have all of that. Now we're looking on the beta factor, for the damping. We have 1% for the structure system. We have 1% for the ceiling and the ducts, and then we have 1% for the paper outfit. So we have a total of 3%. This beta here is going to be helping me out in determination of the acceleration in the vertical direction. You have beta in the denominator. So we're going to be using it there.
Excuse me, sir.
Yes.
Sometimes surrounding environment also has an effect of vibration. For example, if there's a railroad next to the building, it will also cause vibration whenever the train passes on it, right? So
this is correct. Yes. But
in which
this
factor
equation
will
here,
we calculate that?
Yes, but this calculation here in this analysis, considering that there is no other means or methods or sources for any vibration, this is going to be just based on the live load and the people moving on the floor.
But sir, if we have some vibration outside, in which factor will we calculate that? Will we calculate it in beta or in weight or what?
Okay. Are you saying that, let's say that you have another source of vibration adjacent to the building? Is this what you're saying?
Yes, sir.
Okay. So it means the acceleration of the entire place here, this acceleration that we calculate out, if I may go here back a little bit. So I'm going to say I was at slide 41. I'm going to go back to here. Let's just go to the procedure. I'm going to go to this equation, right? This acceleration here, this analysis for this acceleration is just based on this P sub 0 65 pounds, as if this is the thing that's causing the vibration. Now, if you'd like to say that there's another source of vibration, so we need to quantify it and figure out how much acceleration is going to be adding. So let's say that you have additional acceleration here, right? For the entire building, you have one floor, and then you have maybe a rotating equipment that's going to be causing some acceleration. Now you need to isolate that source and figure out the acceleration of it. Now you ask yourself, is there any chance that this acceleration is going to be in the same direction at the same time, which means going to be in phase with the other acceleration?
There may be or may not be.
Okay, what are the chances?
50%.
You don't know. You don't know, because the acceleration also has a direction, right? It goes like in waves. So you don't know exactly when the two waves is going to be in the same direction in the same time. This is going to be very tough to determine this. So maybe you'd like to do square root of summation of the squares, right? So you say square root summation of this acceleration plus the other acceleration. Say most likely this is what I'm expecting, right?
Okay.
Then you compare it to the 5%. So let's say that you have an equipment on the same floor next to this vibration is going to be happening, right? So you know that there is some acceleration in there. And let's say that acceleration there is going to be maybe about 2-3%, right? Yeah, excuse me, like 1/4% or something like this. If this 1/4%, this gives you here the feeling that you don't have the full 0.5% here to consider if you have an office use. So you need to be careful. You need to play with this damping. You need to play with the stiffness of the beam. When you go to stronger beam, now the vibration effect is going to be much less. And then you can combine them and compare it to the 0.5% if you can. In our business here, or in our lecture, and in this course, I'm not going to be covering another equipment, let's say, or another source of vibration with this vibration source. This vibration is going to be based only on the people use. So when someone is using it, you don't want to see lots of vibration.
Okay, thank you, Professor.
No problem. Now, here's the girder information. And again, This is going to be for the beam, the building width and length. And here's the beta factor is going to be 3% that we're going to be using in this equation. So in this equation, we have this at 3%. I said, okay, great. So what's next? What's next here? We're going to be looking at the properties because we need to find out the modular ratio. We need to find out the weight for the beam and for the joist. So for here, E sub T is going to be 2310. I'm not going to be going here through any of the numbers. I'm going to be just walking through it quick. Now this can be the weight here of the deck and the weight of the concrete. As you see here, the weight of the deck is 2 psf. The weight of concrete is calculated out. I don't like to use this method. I'd rather just look it up from our, let's say, catalog, because they give you the exact number. So you shouldn't be doing any approximation, but this is fine. I mean, the way that they're doing here is acceptable for design purposes. So we can say here's the slab weight, and here is the deck weight. This here is going to be the concrete, the solid concrete, and this area here is going to be the amount of fluid that you have in there, which means like the rip in the deck. At the end, you have 41 psf for the self weight of the deck and the concrete slab. Now we need to find out the modular ratio, dynamic modular ratio. This is the one that includes the 1.35. And for that, you have 9.3. And you're going to be seeing now in a minute that this 9.3 is a value that you use. There is no, like, you don't consider it to be 10 or you don't consider it to be 9. You don't do any rounding up or rounding down. You just consider that 9.3 in your analysis. Now you start to take the beam here, and then you take the width, the effective width of the beam for the beam slab, and then you take here, this is going to be minimum of 40%, it's going to be from each side, or S, the spacing. And if you like, I can just take you back here to this. So we're at now slide 44. Let me just take you back to this slide that includes these limits. And here is the slide that includes the limits. When you do here for the slab width, effective concrete slab width, you need to take 40% of L from each side for the spacing. What is L? L is going to be the length, the span of the beam, or S, which means the spacing from each side. 44. So that now you have the effective concrete width. It's going to be the 10 feet, which means the span, the spacing between a beam to another beam. We're going to be taking this width here. We have 3 1/4. We're going to reduce it by a factor of 9.3. Where's the 9.3 come from? It's going to be this factor. So you have your 120. You're going to be taking this 120 divided by 9.3. And as you see here, this number is used as is. There is no reduction. You don't touch it. You just use it as is, right? So it's going to be 12.9. And after that, you do the transferred moment of inertia. So based on this 12.9, now you consider to be a steel section. And then you have IJ is going to be 1840, right? For this beam W18 by 35. Now this is going to be the final value that you use for the transformed moment of inertia. I'm not going to be doing this with you. You guys know how to do it, how to find out the CG of the beam, how to find out the moment of inertia. Now you do the beam mode. Now you need to find out the weight. My understanding is the weight of the beam itself is 35 pounds per linear foot. The weight of the concrete deck and the metal deck is going to be 41 psf. You have additional 4 psf, and then you have 11 psf of the live load. Now this gives you here, and of course 10 feet is going to be the width. So the width, tributary width, multiplied by the weight of the slab of the metal deck, additional dead load and live load. But when it comes to self weight, you don't multiply by 10 of the beam itself. So you have total weight here that you need to consider in your analysis of 595. Again, this includes a little bit of the live load. Now a question, do I need to do load factors like 1.2 dead, 1.6 live load? Andres, yes or no?
I would say yes. Oh, no.
Sir, I don't think we have to do it because they already gave us the total live load and dead load.
Okay, Andres, if you look here at this equation, which load factor have you used for this analysis?
You have
Did we use it? I'm just wondering.
No.
So you don't. What is the reason of this? Do you have any explanation? Today is 19th. Any reason not to consider the load factors? All right, Andres, maybe next time.
No.
This is fine.
Yeah.
Bakri?
Yeah.
What is the reason?
Is it because we're measuring deflection, so we use unfactored weights?
Is this
And
about
calculate-
deflection or vibration?
The vibration.
Vibration. So in vibration, you don't really need the factor loads?
I don't believe so.
Why? How do you feel about this?
I don't believe you have to amplify the loads.
So at what case do you amplify the loads and use this load factors?
When you're testing strength, right?
When you do strengths. So this is not strength check. What would
Right.
you call this kind of check? Do you call this serviceability or what do you call it, or strengths?
Yes, yeah, surfaceability size.
So
That's
in
it.
serviceability, you just use the loads as is, like when you do deflection analysis, which you
Right.
just mentioned a minute ago. So
Yeah.
this is the reason.
Yeah, that's
Right.
yeah.
All right, thanks, Ben.
Mhm.
So we're going to be taking here this load. We'll try to find out the deflection, not because we're doing here a check on deflection. We don't try to compare this versus the span divided by 240 or the span divided by 360. The reason that we have this deflection here is just find out the frequency, natural frequency. So we're going to be taking this load, right, the 595, find out the deflection, consider the transform moment of inertia, right? And for that, I have a deflection of the beam was 0.376. Okay, what's after that? Now we're working the beam mode, not the girder mode. You find out the frequency, and here we go. Here's the frequency. Just be careful about units when you use these equations. The good thing, you have detailed problem here solved for you, because very soon you're going to be doing it in your project. You're going to be doing vibration analysis or vibration check for the beams. You say, okay, now I have this natural frequency for the beam. Now I need to find out, if you remember, the width, the effective width, and the effective weight. So I need to find out the moment of inertia for the slab. And we have seen this before. We know how to do this. This gives you the moment of inertia divided by 12 because I'd like to find it as inch to the 4 per foot. This is exactly what we're doing here. And of course, there's here the n because you'd like to have the same, like to compare an apple to an apple. You'd like to have it as steel material. So this is here a conversion to convert the concrete into steel in your analysis. And then after that, you do here the moment of inertia for the beam, the 1840, transfer moment of inertia. And then you divide here by the spacing between beams. Okay. After this, you do the effective width and the effective beam panel width. You find it out based on the ratio of ds to dj. What is ds again? Moment of inertia for the slab, and dj is going to be moment of inertia for the beam itself. We do this, now we find out the effective panel width. I'm going to take you back here to one slide to let you know which one I'm talking about. I'm talking about this one here. When you talk here about the panel, you think, and then you say how many beams is going to be acting together to support this vibration. And the same thing, they are going to be doing it here for the girder. So if you look here at this equation, Bj, which is the effective width of the beam panel, is going to be equal to Cj. You guys remember Cj? The value of Cj is going to be either 1 or 2, depends on how many sides of slab you have, let's say about each beam. So I'm going to be moving forward to the same slide, 48, that I was just looking at. And here's the value of Cj. Cj is going to be equal to 2. The reason because I have slab on both sides of the beam. Now it's going to be times moment of inertia for the slab divided by moment of inertia for the beam to the quarter multiplied by the beam span. So now I understand that I have 32.2 feet for the beam panel width. So now let me look at this. What is the spacing in this direction here? This spacing is 30 feet. So actually the width of the panel is going to be equal to 32 feet. So I have here, I was able to gauge all beams, all of these 4 beams when it comes to vibration of the beam itself. So, okay, let's see if this is going to help or not. Now you need to check this and be sure that's going to be within 2/3 of the floor width. The floor width is big. You're talking about 150 feet. So I don't see here a problem because you have 150. 2/3 of this is going to be 100 feet. It's going to be greater than 32.2. So the width, effective beam width, is going to be equal to 32.2 feet. This for the panel. Now, I need to find out here the weight. So the weight is going to be equal to the uniform weight, this W. And how much is this W? It's going to be the 595 that we just calculated out, which is right here. If I take you back, 595 pounds per linear foot, multiplied by the beam panel width, B, which is 32.2, times the beam length, which is 35 feet. And of course, you multiply here by 1.5%. And the reason that I'm able here to multiply by 1.5% because I have continuation. Now the girder. I'd like here to work on the girder. On the girder, I'm going to be doing exactly the same thing. But in the girder here, you're going to have a little bit of concrete because the deck direction is going to be parallel to the girder. So when it comes to the beam analysis, when I was doing the moment of inertia, I didn't really need to consider this little bit or this little piece here of the concrete. So when it comes to beam analysis, I just have the deck is going to be running perpendicular to the beam. So there is no concrete here acting normal to the screen. So let me take you back to this beam analysis. So in the beam analysis, I have the deck running right and left. And I don't have any concrete flutes here that sticks down. While in the girder analysis, if I may move here forward, I'm gonna have some flutes that stick down below here, like some webs and stuff like this. So this flute that goes perpendicular to the screen, I can consider it by taking it to be 50% of the total width. So if the girder to girder is gonna be 144, right? And of course, after your analysis, you compare it to the minimum of plus the minimum of. Now we have 144 inches. Within this 144 inches, you have 72 inch, which means half of this 144 at which you're gonna have the flutes. Is everybody clear on this?
Yes.
Sir, can you please explain it again?
Yeah. I'm talking about this versus this. This could be the beam, this could be the girder, right? So in the beam case, like in here, you're gonna see the metal deck and the concrete is gonna be perpendicular to this beam. Like in this case here, right? So when I cut the section through the beam as if I'm cutting through here, right? I'm gonna be looking this way, correct? You see here, if you cut the section through this location, which is right here, there's no concrete below the deck within here. And the concrete is gonna be only within this section. So the concrete is gonna be only here. And this is exactly what we have in the beam analysis, right? So in the beam analysis, we don't have this piece at the bottom. So I said, okay, it makes sense. So in this case, it's gonna be the concrete, and here I have nothing, like what we have done in the beam analysis. If I may go back here and look at the beam analysis, right? Nothing on the bottom. Why? Because you can just simply take a section right here, and this is gonna be the critical section that you need to consider. Someone's gonna say, why don't you cut the section right here? I said, oh, but this in this case, the moment of inertia is gonna be big. But actually, when you look at mini section through the beam here, you're going to see this can be the critical section, and this is going to be controlling your analysis. And this one here, it doesn't make any sense to consider. I said, okay. How about for the girder? You can say, here's a girder section. So in this case, this is going to be here again, the girder section. You're going to see here the concrete is going to be 50% of the concrete through the deck is going to be coming down like this, which means all of this is going to be the concrete that you can consider in your analysis when it comes to the moment of inertia. Why do I know that this is going to be 50%? I'm going to take you back here to the deck analysis or to the deck information. Look at this. You're going to see this here repeated. So this fluid is going to be repeated. It's going to be actually equals to 50%. So this is going to be 5 inch here, and on the top, this is going to be 5 inch. This is going to be in W2. Look at W3. This is from here to here is going to be 12 inch. Again, from here to here is going to be another 12 inches. And this section here is going to be identical to this section here. Also in the W2, this piece or this fluid here is going to be identical to this void area. So this area, this little area is going to be the same as this little area. So when you think about it, you say 50% of the deck width is going to be filled with concrete. And this is exactly what they have done in this analysis. They said, if I'm considering here a width of 144 inch of concrete, 50% of it is going to be filled with concrete within the metal deck itself. If this makes sense now. Are we good?
So, Professor, 72 feet is the concrete for the beam or the concrete due to the slab?
Because of this
I mean,
fluid.
due to the metal deck.
Due to the metal deck infilled concrete.
Okay.
Due to this little piece here. Unfortunately,
Okay.
the system is not going to be that great for this area here. You see this? And for this
Yes,
one
sir.
also. And for this piece. So when you add them up all together, you're going to see that this represents 50% of the width that you'd like to consider of the entire concrete slab.
Okay, Professor.
And this is the reason that we have this
I-
red area here. Now take this width divided by 9.3. This is going to be 7.74. Take the 144 divided by 9.3. What is the 9.3 coming from? Andres, can you help me with this? Andres?
Yeah, looking back at my notes.
Yeah, I'm just wondering, where is this 9.3 that I just said here? What I'm saying is this 15.5 inch is going to be equal to the 144 divided by 9.3. Where do I get the 9.3 from? What is this about?
It's not because of the span, the beam span. No. Yeah, I'm not too sure.
All right. Okay. Thank you. Teresa, can you help me with this?
Well, I was about to say I'm going to help him out. So for that one, it would be the N, which
Yeah,
is because if it's a
it's right here.
composite deck.
Exactly. Thank you, Teresa.
Yeah.
All right. So after you find out the transformed section, then you need to find out the moment of inertia for it. You find out the CG, the centroid, and then you find out the moment of inertia for this transformed girder. So what do you do after this? Here's the transformed moment of inertia. So I'm not going to be walking you through all of these calculations. You can back check it if you like. It's going to be a good practice. And then after that, you start to find out the uniform weight or load that goes to the girder, very similar to what we have done with the beam. So instead of figuring out the point load coming from the beam in your analysis, you can just take an average weight. And then after that, you find out the deflection. And based on this deflection, you find out natural frequency. So the deflection here is going to be based on some weight. And this weight is going to be including all the reactions coming from the side. You just consider to be here a uniform load.
Professor, one more thing. While calculating weight, you added the value of
this one?
Of the girder beam, right?
This one? Yes. This one here includes the slab weight, the beam weight, and the girder weight. This is what the girder is supporting.
Also added the beam section weight? Like
Yes.
W.
Yes, W18 by, which is this W21 by 50 in this case for the girder. You see here, this weight is going to be 50 pound per linear foot. Yes.
But sir, in 595, didn't we add the weight of the beam section?
You'd like, if you like, yes, you can. Yeah. Here it was just ignored, right? But if you like, you can add it. You can add it as kind of uniform load. This would be fine. You're right. It was
Okay.
just ignored here.
Okay.
Okay. After this, you do the frequency, right? The frequency for the girder. And then you do the effective width. Now you need to have moment of inertia of the beam per foot, and then you do moment of inertia of the girder per foot. You remember this C sub G of 1.8? We have 1.8, we have 1.6. You guys remember this issue of the C sub G? Let me take you back here. It's right here in this. Is the 1.6, 1.8 mentioned here? Yeah, here it is, 1.8. If it's gonna be shear connected. If it's gonna be tough flange connected, it's gonna be 1.6. So in our standard business of connecting beams to girders, we use shear tabs. So it's gonna be shear connected. So you use C of G of 1.8. Are very close. So here is a 1.8 factor, which was used in this case. You have the width here. Effective width for this panel, it turned to be 60 feet. Now you need to compare it with 2/3 of the floor length, and the floor length was 105. 105. Where's the 105 was come from? I'd like to hear from Basil.
It's the floor.
Is the floor length really 105 or 150? The floor length.
The floor length is, I have it as.
Where it's come from?
105.
Can you 105? How did you come up with this 105? Can you remind me, please?
So the dimension that is parallel to the beam direction.
Is it parallel to the beam in the direction of the beam or perpendicular to the beam?
Parallel to the beam direction.
Okay, and how much was that? Why did we say 105?
Because in we have 3 bays in the north-south direction, which represents each bay is
Yes.
35 feet, and that's how we got
35 feet times 3?
Yes.
All right, I see. Thank you. Very good. All right, now we need to find out the weight for this panel. Thank you, Basil. Give you a point for this. And is going to be equal to the weight, uniform weight that we are using here. And you're going to multiply it here by B, multiply here by the length. And with that, we have the total effective weight for the girder panel. And we did not increase it by 50%. Anyone recall the reason that we don't include here this addition 50% for the girder? Any reason?
Continuity.
Yeah, because we don't have continuity in the girder. This is correct. All right, now we need to find out the combined mode. So with the combined mode here, we have deflection of the joist, deflection of the girder, and we can use this equation. And you need to be very careful about this units that you use here for gravity acceleration. Now we have the effective frequency of the entire system is going to be 3.99 hertz. Now the length of, it's not the length, actually it's going to be the width of the panel, of the girder panel, turned to be larger than the length of the girder itself. So you can hear some reduction for the deflection of the girder. If you remember that we have here this method of reducing the deflection of the girder, and actually it has been used. So this one you can use it or you don't really have to use it. It's going to be up to you. And in this case, we were able to reduce it a little bit by a factor of 35 by 32.3. And then after that, we do the combined weight. The total weight is going to be based on how much deflection you have in the joist or the beam versus how much deflection you have in the girder. We have done this analysis, right? And the total weight, total effective weight now becomes 109 kips. And then after this, we use this equation. And P sub 0 is going to be the 65. F sub n is going to be the 399 for the combined, which we have just done here. This is going to be the combined frequency. And then we use the effective combined weight, the 109 kips. And with that, I have an effective amplification factor. This is going to be the vertical acceleration. The effective one is going to be 0.0049, which is about 0.5%. So this system turned to be okay at the end. Any questions? Any questions?
Professor, in the mentioned problem, if it at the beginning it says that the cladding will do the bracing for the edge beam, edge girder. If this is not the case, we need to do another analysis for the edge girder.
No.
Find this panel.
Yeah. So in this case here, when you do this analysis, it means that you're doing it for interior beam and girder, but you're not doing it for the exterior case. Because use the exterior case is going to be kind of a little bit tricky when you do it. Okay. So here they are waiving the analysis for the exterior beams and girders. This makes sense to you?
Yeah.
So they said, well, you don't have to worry about the exterior because kind of braced with the exterior skin. This is what they are trying to do.
But my question is, if it's not the case, how we so we need to redo it for the edge girder. So the same we did for
if it is not, and you have been asking to do it, but also this is exactly what I'm going to be doing in my project. When I assign this project, I'm going to say do the interior beam only. So I don't want to push you to do the exterior one. If this makes sense to you.
Yeah. Okay. Thank you, sir.
All right. I'd like to switch gears, and I'd like to hear any questions on this. Good thing you have detailed solved example. So it is going to be that simple. When you go and do your project, you're just going to be going slide by slide and just follow this. Now, what I'd like you to think about and to consider, what happens if I have a system like this, but I have here two concrete walls on each side of the building. Like I have here concrete wall, and not exterior wall, and another concrete wall here. Can you do the analysis to these beams? And what is the fastest way of doing it? How can you do it quick? And do you have a girder? Do you have a girder in this case? Do you have a girder?
No, we don't have a girder in this case.
Do you have combined? Do you have combined mode?
No, just the beam.
So you don't have combined. You don't
we only have to calculate for the beams.
Excellent. This sounds like a good quiz or maybe an exam problem, right? This is gonna be simple, and you can show me exactly if you understand how to use the equations. Okay. All right. Ready to move to next slide set? You guys have this already? Slide set number 9?
Yes, Professor.
All right, great. All right, let's take a couple of minute break before we continue. Right, I'm back. Now we're going to start with the seismic, I'm going to say, topics in this course. You guys, you know the code that we are using when it comes to design. of buildings is going to be the CBC. We discussed this before. We say it's going to be the 2019 CBC. 2019 CBC just adopts the EGCE 716 for the loading, and this way we are taking the load criteria and how do you do the seismic loads, how do you do the dead load and live load, and the load combinations and the whole thing. We'll come to the steel manual. We're going to be using the 15th edition. This is what we're using these days. We'll come to structural steel design. This code here is a section of the steel manual, the 15th edition, the 3.6 and 16. And we have some steel beams and sections that we use here in our analysis when it comes to structural steel resisting seismic forces. You should be able to use the STM grade 36, the A36, 572, 992, it's going to be for the W sections. And for the steel tubes, we use the A500 grade B. All of that, you can use it as seismic members. So great. How about for the seismic design of steel? Because when you look here at this AIC 360, 16, there's nothing there about the seismic. But for the seismic, we have different document. And the document here is going to be the 341, 16. This one also, you can download it for free. It is available. You don't have to pay for it. I'm wondering if you guys downloaded this already. I'd like to hear from you.
Yeah, I have.
Okay, who is not able to download it or didn't download it or didn't know about it?
I'll be honest, I didn't download it.
Okay, do you know how to download it, or can you try now while we are speaking? Because here we are talking about the code. So what I want you guys to try to find a downloadable PDF of it. It is available for free. The AICD put it there for free. Can you try, please, and let me know if you are unable to see it?
And if
Do
anybody
you have a
finds it,
link or something that we can use?
yeah, whoever finds it can put it in the chat.
Quick.
Professor,
Yeah.
did you recently update the PDF copy of this on Canvas? Because mine says 36016 on this slide.
Really? So can
Yeah.
you re-download it again? I'm gonna leave this here, and I can maybe upload it. All right, it's gonna be right there. You just do the search, right? All what you need to do is just to do the search. It's right here. Look at this. Just search for AIC 341-16. It's gonna be the first one on the top. You just click on it. It's gonna start here to download. All right. Are you good about this? I'm gonna save this and upload again. At the end of the day, I'm gonna re-upload this file again so that you guys have the link and just click on it if you like. When it comes to buildings usually is gonna be either one story or multi-story. So here, one story, I just did here one story building, or maybe 3 or 4 or 5 is gonna be the same. I'm just taking here a sample. This system here we call a single degree of freedom system because we consider that the beam moves in one direction. So the beam here is composed of one mass, has like a frame system or something to stop it from moving right and left. Yeah, thank you, Grumbier. Thank you. Yeah. All right, very good. So at the end of the day, this is give you the structure system that you'd like to use when it comes to dynamic analysis. Give you this thing, degree freedom system. So it is true that you may have multi-degree freedom system. What's the difference between multi-degree freedom system and single degree freedom system? In here, you have one mass and one spring and the forces acting on it. In here, you have more than one mass. And also the direction of the movement is going to be different from a level to a level. But at the end, we'd like to convert this multi-degree freedom system into a single freedom system. And the single freedom system, we're going to be considered to be like this, which means if you have a couple of columns, we'd like to consider it to be one column. And this can be easily done because if you have two columns here, this is going to be parallel to each other. So you can just add the values to each other. So at the end of the day, our building is going to be equal to one lumped mass. So this lumped mass here is going to be like a point mass. It is not going to be distributed mass. And for the stiffness, it's going to be the stiffness of this column. We'd like to see it as just one column. And the lateral stiffness is going to be the amount of force that's going to be able to push this column for a displacement of just one unit. If you like to do it as a kip per inch, it's going to be the amount of force that you put here on the top, so that when you push this structure width, it's going to be moving it for 1 inch only. If you like to do it as in kip foot, it's going to be the amount of force that you put in here to push this mass for a foot. Meaning the stiffness, K, is give the force needed to push this mass or the structure for a unit displacement. For us, here's a mass, and instead of having our column, we'd like to summarize it and put it as just a spring. The spring is going to have a stiffness of K. So K is going to be the spring coefficient or stiffness, which is going to be exactly the same definition of this spring or column effect. We'll come to the stiffness here. Now, when this vibrates, it's going to be moving right and left. When it goes right and left, we're going to call this to be our displacement X or delta. It's going to be very similar to what we have here. So if you like, you can also consider this to be your X displacement. So X displacement, it can be right or left. When it goes right, you're going to be extending the spring. When it goes left, you're going to be compressing the spring. Very similar to what you have here. This can be positive or negative. So positive or negative means the direction of displacement. Now, here we are talking about vibration.
In which direction will it be positive? Downward direction?
Any direction, doesn't matter. It's going to be up to you. If I call
so
this
we can
positive,
choose any sign convention.
Yes, it's going to be up to you. But here, in my notes here, I put here to the right, it's going to be the positive. Usually people would like to say when it goes east or to the right side, it's going to be positive. When it goes to the other side, it's going to be negative. But it's going to be up to you. And here's the reason. If I'm looking here at this mass, when the mass here goes to the right, it's going to be positive. When it goes to the left, it's going to be negative. But if you are standing on the other side, and you'd like to use the same convention, you're going to be saying, oh, when it moves right, when you're sitting or standing on the other side, it's going to be opposite to what I consider. If this makes sense. So the positive and negative is not that critical. It's going to be up to you.
Okay.
Now, when this here vibrates, it goes right and left, which means you're going to be pulling the mass and then let go, like what happened in an earthquake. You don't really have an applied force on the structure itself. So we're going to call this to be free vibration. In free vibration problem, you don't have any external force applied to the system. This is why when you look here at this, you say summation of the force equal to 0, right? So this is going to be the external force. External force is going to be equal to 0. And all of this is going to be all internal forces. When you add them to each other, they're going to be equal to 0 in this case. What are the internal forces? Now let me look at this. Internal forces, number one is going to be this inertia forces. What is inertia force? Like the mass time acceleration. Now when this moves, it moves with some acceleration. So if you take this mass, multiply by the acceleration, it's going to be equal to the inertia forces. Also, you have the spring force. When you put this mass to the right, which means in our positive direction, inertia force is going to be opposite because inertia force wants to keep it in place. Also, the spring force is going to be going to the left. Why? Because they're stretching the spring. Also, you have something that we just ignored in this analysis for simplification, which is a damping force. Damping force is going to be similar to that source of damping, like what we have done in our vibration analysis. So for example, when it comes to concrete, the damping effect is going to be coming from the cracking. When it comes to steel, it's going to be also from some minor cracks that happen, and also relocation of the metal particles within the steel beam, and also from the inelastic performance. You're going to have some residual strength, and also it's going to be coming from the partitions, and it's going to be coming from the connections between beams and girder and bolted connection and so forth. So now we know the source of the damping, but you know what? In this analysis, I'm just going to be ignoring it. So I'm going to say if I add here all the internal forces to each other is going to be equal to 0, which means they're not equal to any force because I don't have external applied forces to it. I can write my equation of motion. This F sub I, which is the inertia force, right, is going to be equal to mx double dot. X double dot is going to be acceleration, and m is going to be the mass of the system. The spring force is going to be equal to the stiffness of the spring multiplied by displacement x. And this makes sense because what's the definition of the stiffness? The stiffness is going to be the force per unit displacement. So I can write it here. I'm going to say K is going to be equal to the force divided by displacement by x. And what is the stiffness here? Again, it's going to be the force per unit displacement. Now try to find out the force. The force is going to be equal to what based on this equation? This force is going to be equal to
Kx.
It's going to be equal to Kx. To K times X. This is exactly what we have here in this equation. So it's going to be the inertia force, and this is going to be the spring force. This system here, I consider that there's no damping. This is why you call it undamped system. And because it just vibrates with no external force applied to it, we're going to call it free. Means no external force applied to it. So it's going to be free vibration, undamped system. Let's see here what happened when you don't have any damping. So when you don't have here any damping, look at the performance. It's going to be this undamped single degree freedom system. So in the y direction, you have the displacement direction, right? So you have here the x, the positive, and this is going to be the negative. So here positive and negative is just going to be about the direction. And here on the x-axis, I'm going to have the time domain, which means after 5 seconds, after 10 seconds, what happens? System here, once you pull it to some point, you're going to let go, it's going to start here to vibrate. It's going to be going up and down. And look for this dashed line. There is no reduction in the amplitude. Look at this. It just goes flat. The reason it goes flat, I mean, because there is no damping. And we have gone through this already in the vibration analysis. Going to be adding here some damping and see what happens. Like 5%. Why did I pick 5%? Because the code says usually consider that you have 5% damping for all buildings, regardless of the type of structure that you have in there. Whether you have wood, you have steel, or you have concrete, you consider 5% for the damping effect. We have our natural frequency. Our natural period is going to be really what we care about. So this natural period is going to be very important for us to work with buildings. So a building for me is going to be a single degree freedom system. It's going to be a mass, stiffness, damping is going to be 5%. You don't have control over this when it comes to code design and analysis. And what you need to do is to find out this ratio between the mass and between the stiffness. We call it natural period. Natural period means how much time is going to be taken when you pull the mass to this location and let go. Now what's going to happen? This mass is going to be moved from here, the original location, 0 point, to the other side, come back again. And then we figure out how much time is going to be taken this system to go for one cycle. And we call this natural period. So each building here represents or represented by just one natural period when it comes to our analysis. Great. Now I'd like to work here with buildings. So the building is going to be this rhythm system that you're looking at. You consider here that you're doing experiment or you're doing some analysis. So we have, let's say, a software, or we have experiment if you like, to consider it this way, just for simplicity. And it will start here to shake the base. So the base here is going to be shaken right and left. When the base here is shaken right and left, what's going to happen? This mass here also is going to be shaken right and left. But most likely it's going to be out of phase. Why? Because once you start to push, this is right, this is not going to be moved to the right in the same time exactly. There's going to be some delay or some lag. This is the reason the vibration of this mass is going to be completely different from the vibration of the base. Unless you have a very solid piece of brick. So if you have a big concrete block like this, it's going to be extremely stiff, which means the stiffness is going to be extremely high, like infinity. Now you start to shake the base, the top of it is going to be shaking with the same acceleration. Otherwise, there's going to be some lag between acceleration of the building and acceleration of the base. When it comes to this equation, F sub I is going to be the acceleration of the mass. It is not the acceleration of the base. So this inertia force and this analysis that we are doing here is going to be really based on the acceleration of the mass, not the acceleration of the base. So what happened? We have the earthquake record. And for example, we have this for El Centro, ground acceleration. So it says here 1940 El Centro, earthquake record. And in this case here, we have the acceleration at 270 degrees. So what is a 0 degree? I'm going to say 0 degrees is going to be like this. What is 90 is going to be like this. What is 270 is going to be this one here, which is the same as the 90 degrees. So in this measuring station, we have earthquake records at different directions. And this earthquake record that you are looking at is giving the El Centro at 270 degrees. So I guess now we understand what is this 270 degrees about. It's going to be just one of the measurements that was taken during this earthquake. As I see here, again, the acceleration direction is going to be indicated as possible negative. So negative acceleration doesn't mean that it's going to be like deceleration, but negative acceleration in this case means the direction of the acceleration. You have the right side and the left side. That's why we have negative or positive and negative. Look here, the earthquake was strong for about maybe 40 seconds after this, or maybe 30 seconds after this, just diminishes. It doesn't go right and left with this high acceleration. And the scale that we use here is given in terms of G's. So this is going to be 0.5 of G. And how much is G? If you guys remember, G equals in our units, this going to be, this should be lowercase, G equals 32.2 foot per second square. Okay, this means this is going to be 16.1, this value here. But we'd like to keep it as a fraction of G for our business. The maximum acceleration, now this acceleration, not of the building, this acceleration of the site. Maximum acceleration here was equal to 0.35 times G. We call this peak ground acceleration. So let me write it down here. Let's give you the peak ground acceleration. As you see here is equal to 2.35 G. Now let's see what happened to our structure. So I'm going to play here with the structure Nassau period. I'm going to say, let me bring here a structure. It's going to have damping of 5% because all the structures, when it comes to the code, is going to have 5% damping ratio. And the structure itself is going to have a Nassau period of 0.7 seconds. So the structure acceleration is not going to be matching the ground acceleration. We understand that. But look what happened. At close point, when you have the maximum ground acceleration, look what happened here to the building itself. The building acceleration, we call it spectral acceleration or bending acceleration, S sub A, becomes 0.69, which is almost double the amount of the ground acceleration. So look, the ground itself moves with a maximum acceleration of 0.5, but for the building, it went to 0.69. And look at the performance here. Look at the acceleration. Here is completely different from the acceleration here because of the delay, because of the lag, because they're not in the same phase. So we applied a ground acceleration of 0.35, and we're getting acceleration in the building itself of 0.69 G. I said, okay, let me change here the stiffness of the building, the mass of the building, and let's change here, which means at the end for me is going to be, let's change here the initial period of the building. Now we're going to make it here in a slow 0.7 seconds. We tried 1 second for this building. Now look what happened. Maximum acceleration here becomes 0.51. It didn't really happen the same time with the maximum ground acceleration. If you look here, there's a little bit of delay. Look what happened. So for 0.7 seconds, maximum acceleration of the building itself was about double the amount of the ground acceleration, and it happened almost at the same time. When I go here to a ground acceleration of, when I go here to the same ground acceleration, the 0.35 for El Centro, and I change natural period to 1 second, the building performance was completely different. And the maximum acceleration of the building itself dropped down to 0.5 G, so almost 0.5. And it happened in the other direction, not really in the same direction as a peak ground acceleration. So, okay, how is this going to help me? Now, as I said, the building for me at the end of the day is going to be represented by an initial period. So let's say that you're doing here a new structural steel building. You're going to say, in this case, what natural period do I have for this building? You're going to say maybe 0.3 seconds. So I'm going to say, let's use here the same software. I'm going to bring here the building of 0.3 seconds, put it under this acceleration or under this earthquake record, and see how much is the maximum acceleration that the building itself is going to see. If you have the maximum acceleration of the building, take this, multiply that by the mass, it's going to give you the maximum force that this building is going to be exposed to. Okay. Why don't I try this before I start my analysis? Meaning, why don't I try different accelerations, right? Like in here, different earthquake records with different buildings, and let me play with this. I'm going to say here 0.1 second for my building, 0.2, 0.3, 1 second, 2 seconds, 3 seconds, and 4 seconds. And based on this, I'm going to be coming up with a chart or with this graph. I'm going to call it response spectrum for only 5% for this given earthquake record. And with that, you're going to be getting this dashed line. What is this dashed line? So in this graph, I'm going to have the initial period on the x-axis. So each one of these lines would be representing a structure or a building. Can be drawing it this way. So this means here one building is going to be maybe 2.2. Another building is going to be 3 seconds. Another building maybe 3.3 seconds. Another building is going to be maybe just half, right? Half a second. Another building is going to be a very short period. It's going to be 0.1 second, right? We're going to be trying all of these points and draw the final result, which means this acceleration is going to be the spectral acceleration. So on the y-axis is going to be your SA. So I'm going to say here on the y-axis, this is going to be the spectral acceleration, S sub A. What is S sub A again? S sub A is going to be the maximum acceleration of the building itself, like this 0.69, like this 0.5 G. I'm going to be taking it with each one of this T for the structure and develop this chart. So how this is going to help me? I'm going to say, this is going to be making your life easier, because all what you need to do, if I give you this chart, you look at your building, find out the natural period, and let's say natural period in this case is going to be equal to 1.5 seconds. You just use this chart. You go here is 1.5 seconds. Once it hits this curve, you go left, and with that you have roughly SA is going to be about 0.3, let's say 0.34, right? 0.34 what? This is going to be your SA, 0.34 times G. So in this case, in this analysis, you're going to say SA equals 0.34 times G. So what to do after this? Now you have the acceleration of the building. If the building here happens in this location, at the central location, all what you need to do is to take this SA multiplied by the mass. So it's going to be mass times acceleration. It's going to give you the lateral forces. And this force is going to be the inertia force. And this inertia force is going to be equal to the spring force. So we're going to say, what spring force? We're going to say this force here, according to this equation. This mx double dot that you just calculated out is going to be equal to the spring force. And the spring force is going to be the force that you care about, because this is going to be the force that go through your building. I'm going to stop at this point here. I'm wondering if you guys have any questions, go please and ask. Otherwise, you can sign out. And you guys, you have a good night.
Good night, Professor.
Yes. Right.
Professor?
Yes.
Just wondering about what the advantage would be of buildings that have a smaller natural frequency as opposed to a larger one, a natural period, as opposed to a bigger one, because wouldn't a bigger one just, go through more, or go through the same experience in terms of more time?
More time? What do you mean more time? Natural period, you mean?
The natural period, yeah. The advantages of a smaller natural period.
There's no advantage, but you don't really have control on the building in many cases. So sometimes you're able to control it, but if you have certain number of stories and you have to put certain number, let's say, of shear walls or mount frames or brace frames, so this is going to be kind of controlling the natural frequency that you need to go with. So you don't really have that much of variation that you can work with. For example, if my building is going to be maybe about a second, right? Or maybe 1.5 seconds. I may be able to change it, let's say between 1.4 or maybe 1.3, let's say to 1.7, but not to change it to 3 seconds, not to change it to 0.1 second. So if your building, for example, that you're working with is about 0.2, which happen in many buildings, right? About 0.2, 0.3 seconds, you cannot really make it 1 second, because the benefit of going to 1 second or 2 seconds or 3 seconds is going to be less acceleration, which means less force, right? Less design forces.
Right.
But it is not that flexible. You're kind of restrained here by many variables that you have to use in your analysis.
So you can just design it, per your lateral forces, and then you get the natural period afterwards, and you sort of are just not stuck, but that's what it is based on your design.
Exactly.
Okay.
So you have certain limits, right?
Thank you.
No problem.